Welcome in the second part of this tutorial about Datashare and its new Neo4j plugin. If you've missed the first part of the tutorial, you might want to have a look at the first part. You'll find the link in this video's description. So in the first part, I spoke about Datashare, Neo4j, and how you can use graph databases for your investigations. And so the second part will be a bit more technical, and basically it will be a deep dive into the Enron email corpus data. So the Enron email corpus is a large collection of email conversations, and today we'll use Neo4j and different tools to basically analyze the graph that we've created from this project and try to make sense out of this graph, as well as connect the dots between different entities which are found inside this graph. So thanks for watching, and let's start. So until now we've spoken about creating a graph, but I haven't spoken about the actual data inside the graph. In this tutorial we will be working with the Enron email corpus. To give you a little bit of context, if you don't know about Enron, Enron was a large energy and commodity US company in the 90s, late 90s. It was one of the largest company in the US, and it filed for bankrupt in the early 2000s, actually in 2001, and so this bankrupt was the largest in the US history. And so it was later found during investigation that Enron had been using fraudulent accounting techniques in order to hide losses and boost profit. And so that's it about Enron. And so what is interesting in our case is that during investigations, the emails of the company were seized and later purchased by researchers. And so these researchers kind of reformatted the dataset to make it available for research, and that's what they did. So the Enron, you can access all the Enron emails downloading this dataset, which is freely available. So we've added the Enron email corpus to Datashare, and that's the project that we've indexed on our local version 2, and we will be working with the Enron email data today. To dive into our Enron email corpus data, we'll use different tools. So today we will be using two tools developed by Neo4j. One is the Neo4j Browser, which is a query and analysis tool. So it's the base tool that you use to interact with your graph. Neo4j Browser is distributed as part of the community edition of Neo4j, so it's freely available. And so then we will be using a second tool named Neo4j Bloom, which is kind of a more high-level tool, which lets you interact with your graph in a more intuitive way. And so Neo4j is very powerful, and it's distributed as part of the enterprise distribution of Neo4j, so it's a paid software. So that's the tool we use today. You might want to know that there are alternative tools that can be used to interact with graphs. First one is Linkurious Explorer. So Linkurious Explorer is actually very similar to Neo4j Bloom in that it lets you explore and query and visualize your graph through a nice UI. and it's a very powerful tool. So Neo4j Explorer is a paid software, and if you want to use an open source software, you will be able to export your graph and import it inside Gephi, which is an open source visualization tool. So compared to Neo4j Bloom and Neo4j, Gephi is pretty simple and pretty limited because it's not really Neo4j based, it's just a visualization tool. So you can visualize your graph in an advanced manner, but you won't be able to query it because it's not linked to Neo4j. So that's it. Let's dive into the data. Okay, now let's dive in and use Neo4j's desktop suite to have a look at our graph. So this is Neo4j desktops, and you see that inside it we have the different tools that I told you about earlier, so the Neo4j Browser and Neo4j Bloom. In order to access them, we'll first need to connect to a database. So I will connect to this one, in which I have my graph imported. That's a graph I've imported earlier. And I will open the desktop to have a look at the graph. So here we go. This is the Neo4j browser. So here we are inside our Neo4j browser. So this browser is really the base interface to your graphs data. So in the browser, you can access the different databases which are found on the Neo4j server. Today we'll use this one, which is the one in which we've created the graph from Datashare. So you can see the different kind of nodes here. And the way that we'll interact with this data, this graph, is by writing Cypher queries. So if you're not familiar with Cypher, Cypher is a bit like SQL, but made for graph databases. So you can really think of it as SQL, but made for matching different patterns that are found inside your graph database. So if you remember what I explained in the first part of this tutorial, graph databases are made out of nodes and which are connected through relationships. And basically, writing Cypher is a bit like drawing the pattern that you want to match, and then Neo4j will return you the nodes and relationships matching your pattern. So it's really very intuitive if you come from SQL, because the syntax resembles SQL, and the graph part is also very intuitive because matching data is a bit like drawing the patterns that you are looking for. Cypher is also very powerful when it comes to investigate complex and deep links between entities, because it lets you basically express complex queries in a simple manner. So basically, if you use SQL to investigate links between different entities, different data points, you have to write complex joins, whereas in Cypher you just have to define and match a simple pattern. So it's very intuitive. Going back to the browser, we can have a look at our graph, and I said earlier that the graph was made out of Datashare's document and name entities, so let's have a look at them. If I click here, what the browser is going to do, it's actually generating me a Cypher query matching any document node and returning me a random sample of 25 of them. So here we go. If we have a look at a particular node, we can see that the node has the document label and that it has different properties, and in particular it will have the document title and the document's URL. So the URL is pretty useful, because if we go back to Datashare, to our project, and we copy paste the document's URL after the Datashare URL, we can access this document named due diligence. So this is how you navigate from the graph to Neo4j graph to Datashare. Because when creating the graph, we haven't included the whole Datashare information. We've just included a small set of properties which are useful to explore the graph, but the graph content, the document content stays inside Datashare. So that's how you navigate from Neo4j to Datashare. And so these are documents, but the second kind of nodes that we have are the name entities that we have extracted from the documents. So clicking on the name entities icon, we can now have a look at our name entities, at a random sample of 25 name entities. And if we have a closer look, we can see that we have different kinds of name entities. We have locations in pink, persons in green, and organizations, companies in showing in purple here. And so what you see here, which is interesting, is that actually Neo4j nodes can have several labels. And so in the case of name entity, they all have the name entity label because they are all name entities, but we added an additional label to denote the name entity category. So that's having like multiple labels per nodes can be very useful. And so there is one category of name entities that we are not seeing here, and which are very interesting for the Enron email corpus. It's of course email addresses. So here, if I click, so here the label of email addresses name entities is a bit misleading. It's email, but the email label does not denote email document. It instead denotes email name entities. So that's why we have the two labels in here. And so if I look at a given email, we can see that this node is indeed an email. We have the full address here, the email user in here, and the email domain in here. So that's it for the different kind of nodes that we have in the graph. Okay, so now that we know about the different kind of nodes that we have inside our graph, let's see how they are connected together. So if I pick a random sample of 25 email documents, and that I pick this document, I can have a look at, with the browser, I can expand its neighbors. And so here we are, we can find this email node, email name entity, which is actually the email sender. We have another email name entity, which is the email receiver, and we can see that we have different persons which are probably mentioned inside the email, as well as different organizations, companies. And so this is what the graph we've built is about. It's about connecting the different name entities through documents. And so if we have a look at the different kind of relationships that we have here, we can see that we have three different kind of relationships. We have the appears in relationships, because all of these name entities appear inside this email. And additionally, we have the sent for the emails document. We have the sent and received relationships, which are specific to email. And this is because if we have a look at this email document inside Datashare, we can see that emailed name entities are not actually from the email bodies. So all of these name entities, they were found inside the email body. But these entities, email entities, are actually extracted from the email's metadata. So actually from the email header. And so this is why we have extra information. We have added extra information for email senders and recipients, because we have a relationship which is a bit more specific than the regular PSIN relationship. And so this is the structure of our graph. Okay, so now let's navigate inside our graph using the Neo4j Browser. So the browser lets you actually navigate inside your graph by expanding nodes neighbors. So that's what I've done here. It got a bit messy quickly, but basically expanding these nodes neighbors. So this node, remember, this node is an email address. I can see that it exchanged a lot of emails with this other person. And so if I pick another of this email, I will be able to see other name entities found inside it. So let's do it. I see that this email was actually sent by this person and received by these 3 persons. And that one person named Ben was actually found inside the document content, and so Ben is probably this Ben that we have here. So that's what the graph that we've built is about, is really connecting entities together through the different documents that are found inside Datashare. And so, for instance, I can have, okay, so maybe let's clean things a bit here so that it looks a bit nicer. So here is our document, and one thing that I could do in here is just try to see if some organization is also cited in other emails. So here we have a company which is PG&E, and we can see that it's cited, it's connected, it's cited in many emails, and so it's probably connected to a lot of other name entities. So here we can see that thanks to the connection which is made by documents, all of these name entities that we can see here are connected together, and so that's how that's what's interesting in our case, since we want to investigate the links between different entities inside our Datashares project. So earlier I have explained that the browser was the base tool to interact with your graph, and that we were using the Cypher language to interact with it. So now let's do a little bit of Cypher. So I've saved some Cypher queries in it, and so actually let's run some analysis on our graph. So this is what Cypher looks like. I'm not going to go into detail, but basically I'm using Cypher to match email documents, email addresses, sorry, which appears inside documents, and then I'm running some aggregation here to actually count how many times a given email domain appears inside my database. So let's run the query. Yeah, you can see that it's running here, and it should return in a few seconds. And so here are my different email domains ordered by number of appearance, and without surprise, we can see that the top domain inside my database is Enron.com, because remember that the Enron email corpus is a corpus of emails exchanged by Enron employees. So what we can see in here, we can see that not only employees exchange emails between them, but they also exchange email outside of the company. And so that's why we have all these different domains in our corpus. Okay, so now that we've seen the different domains inside our dataset, one thing that we could do is try to focus in a particular one. And so reading at the Enron email scandals Wikipedia page, I could see that actually the Archer Anderson accounting firm was in charge of auditing Enron at the time of the scandal. So one thing that we could ask ourselves is, was the auditing company aware of Enron's fraudulent techniques? And so if we want to find out about it, we need to have a look at emails between Enron's employees and Archer Anderson's auditors. So that's what we are going to try to do. So let's try to focus a bit on Archer Anderson. And so the first thing that we want to do is to see if there are what are the different email domains which belong to the Archer Anderson auditing firm. So for that, I have written a simple Cypher query, which is matching all email addresses, and basically aggregating all email addressing, like returning the distinct email domains which contain the Anderson word. So if we look at it, we can see that the query is actually returning several email domains. If we want to focus on conversations between people at Archer Anderson and people at Enron, we will have to look for all emails having the Enron.com domain as well as one of these domains. So luckily for us, all of these domains are pretty similar. They all end with Anderson.com. So this is why next I have written a Cypher query, which is actually going to return me all conversations between people at Enron and people at Archer Anderson. And so we can see that for this, I wrote this simple query, which is matching a path of email address node, which sent a document, so an email document received by an email recipient, email address recipient. And so in order to restrict, so if I just return there without specifying anything, this will just return me all of the nodes that I've seen earlier. I mean, all of the emails addresses and emails documents that I've seen earlier. So that's why here I've added a small constraint on the path so that only the only path which will be returned will be the one where the sender is actually someone at Enron and the recipient is someone at Archer Andersen, or the other way around. And so if I run this Cypher query, you can see that it's returning me a subgraph which should only contain exchanges between people at Enron and people at Archer Andersen. And so this subgraph should be of interest if I was to investigate whether or not people at Archer Andersen were aware of the fraudulent techniques used by Enron's employees. So actually, I'm not gonna dive into this topic, and I'll instead be jumping to Neo4j Bloom, which is another tool that we can use to explore a graph. So let's get started. To access Neo4j Bloom, we go back to the Neo4j desktop, and then just like we opened the browser earlier, we're gonna click here and open Bloom instead. And so we land on this page, which is the Bloom's homepage. So Bloom's homepage will show you your perspectives. So quickly, what are perspectives about? If you have a single graph, a single database, you might have different kind of nodes inside it, and depending on what you're trying to investigate, it might not be relevant to see all of them. So you might want to focus on a small subset of nodes and relationships, and so that's why that's what perspectives are about. They are a certain view that you can define to analyze a certain aspect of your graph database. And so for this demo, we have a single perspective in which we've included all of our named entities and document nodes. And so the first thing that you do in Bloom is to define what are called perspectives categories. And so basically a category is a set of labels. So here I have mapped each one of my name entity labels to a category with the same name, but you could choose to decide to group several nodes labeled into a single category, if that makes sense, for your perspective. And so you can see that when you create the categories, you're given the ability to choose a name for it, and so that can be convenient. For instance, here I have renamed the document label into email documents categories to make it less ambiguous, because as we said earlier, we have the email name entities which are labeled as email. And so here I have labeled these name entities into email address, into the email address category, which might, will make things a bit less ambiguous. Next thing that we can do in Bloom is to actually style our perspectives, and styling the perspective is just about deciding how your nodes will look like. And so I have assigned a different color and different icons to my different categories. And so so this is how you define the Bloom's perspectives. So now let's have a look at our graph the same way as we did earlier. So let's pick random sample of name entities and documents. So for this, we can use the Bloom search bar on the top of the screen, top left of the screen, and just as we did earlier, I can try to have a look at a random sample of email documents, and here we are. We have a random sample of 1000 documents. Just as earlier, we can check the documents, the nodes property. And one interesting thing that we can do with Bloom is actually to just expand or at least check at one node's neighbors. And so doing this will allow us to navigate in a much more fine-grained way as earlier. You remember that earlier when I was clicking on a node, all of its neighbors were expanding, but here, if, for instance, if I have a node with a lot of neighbors, I can decide to expand only to some of them. So that's what I'm doing here, and so this allows me for a much more fine-grained navigation than when using the browser. One extra thing that I can do is to navigate to new nodes through relationships. And so the same way as I've just done it, I can decide to only navigate to the person who sent the graph. Sent the email. So you see that it's just as we did earlier with the browser, but Bloom offers you more control on the way that you can navigate. Another way to navigate inside Bloom is to use expansion. So let's try to find a nice email with a reasonable number of name entities. So this one seems nice. So clicking on expansion, I can try to expand only the sender of this email. And the same way I can expand only to the recipient. Or if I choose, I can also expand all nodes at one time. So same as earlier, Bloom lets you have a fine-grained way to navigate inside the graph, which is nicer than what we did earlier. Remember, in the browser, when clicking on some nodes, we had all the nodes popping. That's it about navigating inside Bloom. So until now, we've been looking at the email address nodes, people at Enron pretty randomly, and if we knew nothing about this graph, what we would like to do is actually to kind of focus on the most important nodes. And so to do so, what we would do is to use data science. And in particular, we would use the Neo4j Graph Data Science library using some of the algorithms which are offered by the library. And in particular, we would use centrality algorithms. Centrality algorithms are a family of algorithms which are supposed to assign a score to central nodes. I mean, they will assign a score to all the nodes inside our graph, but they assign a higher score to central nodes and a lower score to nodes which are less connected. So what we name central in the graph is a node through which a lot of information flows. So, for instance, in our email graph, a node which will be considered central if it sent a lot of emails and that this node also sent email to a lot of person. And so using this centrality algorithm, we can expect to kind of identify who were the main characters at Enron. So of course we know it because we can read it on Wikipedia, but if we were discovering about a new dataset, this could be very interesting. And so let's apply some data science. So for this I will go back to the browser and I will run this script. So in this script that we're going to run against our database, we have two parts, which I will be explaining quickly. We will be doing two main operations. The first one will be using the Graph Data Science library to project our graph, and I will explain why it's important to do so later. And then we will be using our PageRank algorithm, which I'll also detail later, to assign a centrality score to each one of our nodes. The higher the score, the more central the node will be. So let's have a look again at our graph and try to understand why we are using a projection. So if I have a look at, if I pick a random email in here, we can see that this email has been sent by an email address, and that it has been received by many of them. And so the idea here is that entities are connected together through documents. But in my case, what I want to do is to assign a centrality score to entities only. I don't want the email document to be part of what I will score. So this is why we are going to use the GDS projection, and so basically the projection is about transforming this kind of relationships, so a sender sending an email document to a recipient, so it's indirect relationships with three nodes, and so this path is composed of three nodes and two relationships. So we're going to transform this kind of path inside a graph into simpler and direct relationships. So the email sender will directly be connected to the receiver, and actually we are going to aggregate all the emails sent inside the newly created relationships property. And so actually what if we look back at our graph, these nodes will be these two nodes will be directly connected to this one, and this is the graph we are going to run our PageRank algorithm on. So now, what is the PageRank algorithm? The PageRank algorithm is a centrality algorithm, and it will try to surface the most important node that we have inside our graph. So let's dive a bit into the PageRank. Okay, so I've selected the subgraph here, which will help me give you an intuition what the PageRank centrality algorithm is about. So let's say that this is our graph, and the way the PageRank works in order to identify what are the most central nodes is by doing what we call a random walk inside a graph. So for instance, if I pick a random node inside a graph, let's say this one, the PageRank will actually follow the nodes, a random node connection to navigate to another node. And so if I land on this node, since there's only one relationship, I will land automatically on this node in blue in here, and from this node I will pick a random other node, which can be this one, and so on. So from this one I will go back to the blue node, and from the blue node I will pick a random node, which could be this one, and so on. So doing this, if I keep track of which node I have visited, so each time I get inside a node I increment a counter, and that I do a lot of iteration of this random walk, what is going to happen is that nodes which are the most central, so will receive a higher count. And so this is kind of intuitive. You can see that this node is strongly connected to the other one. So if I land on a random node in this part of a graph, I have a very high probability to come back to this node. And so this node will end up having a high PageRank score, where these nodes here, which are more peripheral, and a bit less connected, will have lower nodes. These nodes here, which are kind of more connected than these ones, will probably have a higher score, and so on. So PageRank is a really simple algorithm which operates a random walk into a graph, and which will just count how many times nodes are visited. And so if I go back to my script here and that I run the PageRank algorithm, I'm getting an error, of course. So let's see what it's about. It's about a typo. So let's fix this typo. I guess it's in here, and run the algorithm. So this time it's running, and now when the algorithm has run, I can expect my nodes to have a PageRank property which will reflect the centrality of my nodes. So let's have a look at it. So in order to visualize the most central node in the database, what Bloom lets me do is actually to add a search phrase. So earlier we've been using the search bar and we've used patterns to return documents, but here what Bloom lets you do is actually to define Cypher queries that you will be able to access inside the search bar. And so I've defined a search phrase to have a look at the top n most central email addresses inside my graph. So if I use this saved Cypher search phrase to return me the 100 most central email address, here they are. But this is still not very useful because they all look the same. So one additional thing that I'm going to do is to actually style my perspective and create a rule to have all of these email addresses look bigger if they are more central and look smaller if they are a bit less central. So this is what I'm going to do here. I'm defining a range based on my PageRank property, and now I am scaling all of these nodes size to how to their centrality, so that most central email addresses will look bigger. And so if we look at the largest one, it's Kayleigh, who was the CEO of Enron at the time. So of course this person is central, but there are some other addresses which are quite central. For example, Jeff Skilling, who also is somewhere in there. So yes, we can see that so this is another email address of Kenneth Slay. So we can see that here, if we knew nothing about our data, the graph data science would and the centrality algorithm would have helped us to kind of quickly get another view of who were the most important person inside our graph. Okay, so earlier I have shown how we could use the expand functionality to navigate between nodes, which is nice, which offered a much more fine-grained way to navigate between nodes than in the browser. But actually, we can do better. And so this will be done using another Bloom feature, which is the scene actions. So scene actions are just like the search phrases that we've used earlier. They are custom Cypher queries, but instead of executing it from the search bar to return nodes, we are going to apply the scene actions on the top of a search. So basically here I have a search result, and I'm gonna perform some actions on the nodes to have a like fine-grained control of the navigation and of the information that I am displaying. And so the first action that I've defined is an action which displays the emails which are sent between two nodes. This was not really doable in a scene when using expansion, because when we expand node, it's done in a differentiated way. So even if I use advanced expansion, there's no way to specify who will be the recipient of the email. So for instance, if I want to have a look at the emails between Sarah Shackleton and Tana Jones, I can use these actions, which is triggered like this, and you see that I see only the desired emails. So this is pretty neat. And one more thing that Bloom lets you do when you have this kind of exchanges is to actually slice the information and to display it interactively based on a range. And so, for instance, I can have a closer look at the email exchange between these two email addresses based on the time. So you see that I have created a range on the email creation date of the email nodes, and it created me a slicer which actually let me restrict the nodes that I'm seeing in this view, and will dynamically adapt the view based on the value of the range. And if you want to, you can also use this range or this functionality to basically display the exchanges between two email addresses throughout time. So this is pretty neat. So that's it for this first scene action feature. So the next scene action that I have defined is actually kind of the opposite that we've done earlier. Earlier we've expanded the graph to see all email addresses between two selected addresses. Here, what I will want to do is not the opposite, but if I want to offer a compact representation of the exchange between email addresses, what I will need to do is to apply kind of a projection. So just like we did earlier during our PageRank algorithm, I can be interested to see the exchange between email address nodes, but without the email nodes between them. So that's why I have created this scene action in here, which will, just like we did for the projection earlier, will transform relationships with the email address in between the sender and the recipient into a single relationship. So if I use this action on this graph, this is what I get. So it's a pretty compact representation, which is kind of readable. I mean, it's not great, but it's fine. If I had done the same, but with the emails nodes in between, it would be unreadable. So here we can see that if I look at the relationship, the projected relationship, we can see that the number of emails exchanged between the two addresses appears as a property. So this is a pretty handy action. And the last scene action that I have defined is about displaying exchange between specific email address nodes and people at the Arthur Andersen auditing firm. So if you remember correctly, earlier we've seen that Arthur Andersen was the company in charge of auditing Enron at the time of the scandal, and so we could be interested to see if among the top executive at Enron, who was in charge of exchanging with people at Arthur Andersen, at the auditing company. So that's why I've created this scene action in here, which basically will expand the graph to the auditors' email addresses for the node that I have selected. So if I select all of my top 25 most central nodes, and I'm looking for the exchange with auditors, this is what I get. So here I have returned 100 nodes, I think, but I can return a little bit more of them. So let's try again with more nodes. And what we can expect to see is that some executive will be strongly connected to auditors and some a bit less. And so this is what we get. We can see that some people were exchanging a lot with people at Arthur Andersen, and some other person were actually not even exchanging with them. So if we were to investigate suspicious contability practices, we would focus on these particular nodes and these particular persons. And so if we look at who was exchanging a lot with auditors, we can see that Kenneth Slay was of course involved with them, but we can also see people like Vince Kaminsky or Gerald Nemec. On the opposite side, some of these persons were not very connected with the auditors. And so that closes our tour of Bloom scene actions. So now we are going to move to more data science. Earlier we used the centrality detection algorithm to surface the most important nodes inside our graph, and next we'll be using community detection algorithm. So community detection algorithms are meant to detect identify the different communities that are inside your graph. So communities are groups, clusters of nodes which are strongly connected together, And so we can expect nodes inside the same cluster, inside the same community, to have a high exchange rate, or at least to have an exchange of information which is higher than with nodes which are outside of the community. So that's what we call communities. And so applying the community detection algorithm is interesting because each might lets you discover about the different kind of entities that you have in your graph, or at least the different groups of entities that you have in your graph, because once you know about the different groups of people that are inside a company, you can, for instance, try to focus on a subset of them and have a kind of fine-grained investigation. So let's dive into community detection. So we are back in the browser to apply the community detection algorithm. Here we will be applying the Louvain algorithm. And so the same way as we have used a projection earlier to focus only on relationships between email sender and recipient, we are going to project the graph to transform this indirect relationship into a direct one. And then after that, we are applying the Louvain community detection algorithm, which will apply the same Louvain ID to nodes of the same community, same cluster. So this is a clustering algorithm. So here we go. The algorithm is running, and now we should have nodes. We should have yes, Louvain ID inside our nodes. And so we can clear our scene and try to display, just like we did earlier, we can try to display the cluster by using a custom rule for our email address nodes. So this time, like instead of scaling our nodes based on the rank, we are going to use the Louvain ID that we've just defined to display nodes of the same cluster with the same color. So this is the second rule that I'm doing here, and I've applying it. So we can see that my nodes are changing colors, and so all these nodes in purple, they belong to the same cluster. So now let's dive a bit into the relationships between these nodes to see if the clusters are correct. If we display the exchanges using the action that we've defined earlier, we can see that actually nodes with the same colors tend to be on the same side of the graph. So here I have a purplish cluster. The orange nodes tend to be on that side of the graph, and the red nodes are also kind of close together. And so so these are the different communities that I see in my graph. And what is also noticeable is that if we look at the exchange between nodes of different communities, so here the green community and the purple community, we tend to have a low exchange rate, whereas if we look at nodes of the same community, we see that there's a high exchange rate. So yes, this is what community detection is about. It's about really detect communities, clusters of nodes which are strongly linked, tied together, and weakly, loosely linked to the other communities, to the other nodes. And so you might wonder what these kind of algorithms are useful for. Usually, the community detection algorithms are really used to get an overview of the different types, groups of entities that you have inside your graph. And so when you start an investigation, this can just help you to know who are the different groups of people inside a company, and so on. And so this will help you have, for example, this will help you narrowing your investigation, because you might choose to investigate some communities while you might judge that some other communities are not of interest. And so that's it about community detection. One last very useful and nice feature of Neo4j Bloom is the search bar. So we've used it a bit earlier, but not to the fullest. If you remember, when we were using the Neo4j Browser at the beginning, not really at the beginning, but towards this query, we were trying to display a subgraph of exchanges between people at Enron and people at Archer Andersen, which is the main auditing company of Enron. So now we will try to use the search bar to actually do the same, because here we have written some Cypher query, and actually Bloom lets people who are not really familiar with Cypher actually perform pretty advanced queries. So if I'm interested in this subgraph that we've seen right here, I can use the search bar and look for some patterns. And so if you remember about the pattern that we've seen earlier in the browser, we have been looking for email documents which were we were looking for email addresses which received email documents sent by the people at Archer Andersen. So all of these people, they have an email domain ending with Andersen.com. And so sorry, this one is not right. It's the email domain should end with Andersen.com, not start with. So here we go. Let me remove the Louvain clusters. So here we have done one side of the query. So this one, email sent by people at Archer Andersen, and we can do the other way around. So look for email addresses who sent email documents received by people with address email which domain is ending with Andersen.com. And so this will give me the other part of the graph. And so here, with these two patterns that I've matched, we can expect to retrieve kind of the same graph that we've retrieved here using Cypher. And so this is pretty nice, because it means that if you're not familiar with Cypher, you can still use Neo4j Bloom and perform pretty advanced searches. So that concludes our Bloom's tour, as well as our tutorial. I hope that you enjoyed the video and that I convinced you that Neo4j and Datashare they fit well together when it comes to investigating relationships between entities inside investigations documents. So this is the first Neo4j feature that we are integrating inside Datashare, and there will be many more coming in the next year. So please share your feedback, and also let us know if you would like to see some specific graph-based feature inside Datashare. It will be very precious feedback. Also let me know if you have any question concerning this tutorial. I'll try to answer you, and thank you for your attention.